We will now study the Laplace transform, which is actually the fifth unit in mathematics 2. All the transforms in mathematics is used for only one purpose. It is used for converting one mathematical model into a different but equivalent model. The model which we are reducing from the existing model will be very easy. The famous example that you have already seen is logarithm. Logarithm, it converts multiplication into addition and division into subtraction. Subtraction is more simple than division. Similarly, addition is more simple than multiplication. So using transform, we can reduce the existing mathematical model into a different but very simple model. So here also the Laplace transform is used for that purpose only. The ultimate application of the Laplace transform is to solve ordinary differential equation. Even though we have studied a lot of models, methods to find the solution for an ordinary differential equation in our higher secondary, this Laplace transform is uniquely used for the purpose of solving ordinary differential equation. What Laplace transform does means it converts the given ordinary differential equation into an algebraic equation. From that algebraic equation, we can get the solution of the ordinary differential equation in a simple manner. That is the application of Laplace transform. So here also we are studying the Laplace transform in mathematics 2 for solving ordinary differential equation ultimately. So now we will start the Laplace transform with the formal definition. You take a given function f of t. F of t is any function of t which is defined for all values of t greater than 0. That is, it is defined from the interval 0 to infinity. The Laplace transform of f of t is defined by integral 0 to infinity e power minus st f of t dt. Here s is a parameter. It may be a complex constant or simply constant. The Laplace transform of f of t is denoted by L of f of t. That is, L of f of t equal to integral 0 to infinity e power minus st f of t dt. The integration is with respect to t. Therefore, the limits 0 and infinity are for t. After evaluating this integral, we will get a value of this integral in terms of s. So whatever the value of f of t may be, the value of the integral will be always a function of s. That's why we can denote the value of this integral also by some f of s. So L of f of t is equal to integral 0 to infinity e power minus st f of t dt, which is also denoted by capital F of s. So now using this definition of the Laplace transform, we will derive the Laplace transform for certain standard functions. For example, let us take a function c, where c is constant. Let us see how to find the Laplace transform for c, where c is constant. Now, by definition, L of f of t is given by integral 0 to infinity e power minus st f of t dt. To find L of c, we have to take f of t equal to c. So in this case, we get L of c equal to integral 0 to infinity e power minus st c dt. You just take f of t equal to c. So here, since c is constant, it can be taken out from the integral. So we get this integral is equal to c into integral 0 to infinity e power minus st dt. If you integrate e power minus st with respect to t, you get e power minus st by minus s. Integral e power ax dx equal to e power ax by a. So therefore, the value of this integral is equal to this. Now we apply the limit, upper limit infinity. If you put t equal to infinity, this power becomes infinity. Similarly, if you put t equal to 0, the power becomes 0. So we get c into integral c into e power minus infinity by minus s minus e power 0 by minus s. The value of e power minus infinity is 0 and the value of e power 0 is 1. So ultimately we get c into 0 minus 1 by minus s, which is equal to c by s. So therefore, what we have derived here is the value of L of c, where c is constant. So L of c equal to c by s. Suppose if c equal to 2, then L of 2 will be 2 by s, L of 10 will be equal to 10 by s. So like that you can find the Laplace transform for any constant. Let us take up the Laplace transform of another standard function e power at. L of e power at by definition is equal to integral 0 to infinity e power minus st into e power at dt. You take f of t equal to e power at. So while multiplying e power minus st and e power at, you can add the powers. So this will be equal to e power minus st plus at dt. And from the power, if you take minus t outside, you get integral 0 to infinity e power minus of s minus a into t dt. This integral is also of the form integral e power ax dx. So its value will be e power ax by a. So here the constant a is minus of s minus a. So after evaluating this integral, we get e power minus of s minus a into t by minus of s minus a, limit 0 to infinity. If you put infinity, the numerator becomes 0, e power minus infinity becomes 0, and if you put t equal to 0, the numerator becomes 1. So ultimately we get 1 by s minus a. So the Laplace transform of e power at equal to 1 by s minus a. This is another standard result. So like that we can find the Laplace transform for the remaining standard functions, like Laplace transform of sin at will be a by s square plus a square. Laplace transform of cos at is s by s square plus a square. Laplace transform of sin h at is a by s square minus a square. Laplace transform of cos h at is s by s square minus a square. And finally the Laplace transform of t power n, where n is an integer, which is equal to n factorial by s power n plus 1. So these are all the standard results using which we will solve some problems, because these results are very, very important. So now let us take up few examples using these standard results. First let us take up the Laplace transform of e power minus 8t plus cos h2t plus sin 7t. So Laplace transform of this expression will be equal to Laplace transform of the first term plus Laplace transform of the second term plus Laplace transform of the third term. The first function is of the form e power minus at. Its Laplace transform is 1 by s plus a. Here a is 8. So the value of the first term is 1 by s plus 8. Similarly, Laplace transform of cos h at is s by s square minus a square. Here the value of a is 2. So we get the value for the second term as s by s square minus 2 square. Similarly, the third function is of the form sin at, where a equal to 7. So its Laplace transform is a by s square plus a square. So like that, by using these results, you can get the Laplace transform for any standard function or combination of any standard functions directly. Let us take up another example. Find the Laplace transform of 7 e power 2t minus 9 e power minus 3t plus 5 cos t plus 7t cube minus 5 sin 3t plus 2. The Laplace transform of this expression will be equal to Laplace transform of the first term minus Laplace transform of second, etc., etc. So now let us see the Laplace transform of each and every term one by one. So here in the first term 7 is constant, so you can keep 7 as it is. 7 into Laplace transform of e power 2t. The Laplace transform of e power 2t is 1 by s minus 2. In the second term 9 is constant, so minus 9 will come as it is. So minus 9 into Laplace transform of e power minus 3t is 1 by s plus 3 plus 5 into Laplace transform of cos t is s by s square plus a square. Here the value of a is 1, so 1 square will come here. Similarly, 7 into Laplace transform of t cube is 3 factorial by s power 3 plus 1 minus 5 into Laplace transform of sin 3t is a by s square plus a square, that is 3 by s square plus 3 square, plus finally we have a constant here 2. So the Laplace transform of 2 equal to 2 by s. So this is the Laplace transform for this expression. Let us take up another example. Find Laplace transform of t plus 1 whole square. Now we expand t plus 1 whole square using a plus b whole square formula. It is equal to a square plus 2ab plus b square, that is t square plus 2t into 1, that is 2t plus b square is 1. You can take the Laplace transform term by term. Laplace transform of t square plus Laplace transform of 2t plus Laplace transform of 1. Laplace transform of t square is 2 factorial by s power 2 plus 1. In the second term 2 is constant. We have L of t. L of t is 1 factorial by s power 1 plus 1 because the power of t is 1. So 1 factorial will come here. And the last term is constant. So Laplace transform of constant is constant by s. So like that you can find the Laplace transform very easily. So 5 problems, very simple problems are given for your practice. So using the standard definitions, standard results, you can find the Laplace transforms for these functions. Now let us take up one important property known as first shifting property. It states that if L of f of t equal to capital F of s, then L of e power at into f of t will be equal to capital F of s minus e. What does it states mean? It states that L of e power at into f of t will be equal to L of f of t when s tends to s minus a. That means for finding the Laplace transform for any function of type e power at into f of t, what you have to do means you have to find the Laplace transform for f of t only. By ignoring e power at, you just find the Laplace transform for f of t, that is L of f of t. In that result, you replace s by s minus e. Similarly, if it is e power minus at into f of t, the Laplace transform of L of e power minus at into f of t will be L of f of t when s tends to s plus e. So this is about the first shifting property, and proof is very simple. You know, by definition of Laplace transform, L of f of t equal to integral 0 to infinity e power minus st f of t dt. It is given as f of s. So here s comes, so you can denote this integral by f of s. Now we want to find the Laplace transform of e power at into f of t. So you take e power at into f of t instead of f of t. You just take e power at into f of t in the place of f of t. So what do you get by using the definition? So the Laplace transform of this will be equal to integral 0 to infinity e power minus st into the function given, which is nothing but e power at into f of t dt. So these two, e power minus st into e power at together can be taken as e power minus of s minus a into t dt. Now you compare these two integrals. So if s comes, we denote the integral by f of s. So here in the place of s, what we have here? We have s minus a. So therefore, using this assumption, you can denote this integral by f of s minus a. So the proof of the first shifting property is very simple, but you should understand the result of the statement of the first shifting property. It actually gives the Laplace transform for any function of type e power at into f of t or e power minus at into f of t. Clear? So now let us take up a few examples using this first shifting property. Find the Laplace transform of e power 2t into cos phi t. So the given function is of the type e power at into f of t, where f of t equal to cos phi t and the value of a is 2. Clear? So according to first shifting property, to find this Laplace transform, we have to find the Laplace transform only for f of t, and in that result we have to take s is equal to s minus 2. So therefore, by first shifting property, Laplace transform of e power 2t into cos phi t equal to Laplace transform of cos phi t, where s tends to s minus 2. So which is equal to, what is Laplace transform of cos phi t? S by s square plus phi square. So in that you put s is equal to s minus 2. So you get s minus 2 by s minus 2 whole square plus phi square. Similarly, let us take up another example. Find L of t square into e power minus 2t. So L of t square into e power minus 2t, for our sake of convenience, it can be taken as L of e power minus 2t into t square. Now it is of the form e power minus at into f of t, where f of t is t square. So according to first shifting property, this will be equal to Laplace transform of t square when s tends to s plus 2. So Laplace transform of t square is nothing but 2 factorial by s power 2 plus 1, where s tends to s plus 2. So the value of 2 factorial is 2, denominator is s cube. You put s is equal to s plus 2, you get s plus 2 whole cube. So the value of this Laplace transform is 2 by s plus 2 whole cube. Let us take up another example. Third one, find L of e power minus t into 3 sin h2t minus 5 cos h2t. The given function is of the type e power minus at into f of t, where f of t is this. So using first shifting property, let us first find the Laplace transform for f of t. That is Laplace transform of 3 sin h2t minus 5 cos h2t. In that result, we have to take s is equal to s plus 1. So in the first term 3 is constant, and Laplace transform of sin h2t is a by s square minus a square. Here the value of a is 2, so 2 by s square minus 2 square minus 5 into Laplace transform of cos h2t is s by s square minus 2 square. Now you take s by s plus 1. So you get 6 by s plus 1 whole square minus 2 square is 4 minus 5 into, replace this s by s plus 1. So you get 5 into s plus 1 by s plus 1 whole square minus 4. This is the Laplace transform. So using the first shifting property, you can solve these 4 problems. Next, let us take up a theorem. It states that L of t into f of t equal to minus d by ds of L of f of t. That means whenever the function is of the type t into f of t, using this result we can find the Laplace transform. So the t under the Laplace transform is changed into minus d by ds. If it is t square, it will be changed into d square by ds square. If it is t cube, it will be minus d cube by ds cube. So to find Laplace transform of t into f of t, we have to find the Laplace transform of f of t alone. This Laplace transform should be differentiated with respect to s with negative sign. So using this theorem, we will see few examples. First, let us take up the Laplace transform of t into sin 2t. According to theorem 1, L of t into sin 2t will be equal to Laplace transform of sin 2t. This Laplace transform should be differentiated with respect to s with negative sign. So L of sin 2t is 2 by s square plus 2 square. So you differentiate this with respect to s and assign negative sign finally. So now this is of the form u by v. We know derivative of u by v is v into derivative of u minus u into derivative of v by v square. So using the quotient rule, if you differentiate this, we get 4s by s square plus 2 square whole square. Let us take up another example. It is very important one. Find the Laplace transform of t into e power minus 2t into sin 2t. Look at the given function. We have a function which is a combination of 3 different functions: t, e power minus 2t, sin 2t. So you just consider this function. You can assume that this function is of the type, since the leftmost function is t, you can assume that this function is of the type t into f of t, where f of t is e power minus 2t into sin 2t. So according to theorem 1, L of t into f of t equal to minus d by ds of L of f of t. So this t is changing into minus d by ds. For the rest, we have to take the Laplace transform, L of e power minus 2t into sin 2t. How do you take the Laplace transform of e power minus 2t into sin 2t? Now this e power minus 2t into sin 2t is of the form e power minus at into f of t, where f of t is sin 2t. According to the first shifting property, L of e power minus at into f of t will be equal to L of f of t, where s tends to s plus 2. So this Laplace transform will be equal to Laplace transform of f of t. Here f of t is sin 2t, where s tends to s plus 2. So you take the Laplace transform of sin 2t, which is nothing but 2 by s square plus 2 square. So in this you replace s by s plus 2. So we get 2 by s plus 2 whole square plus 2 square is 4. If you simplify this, you get s square plus 4s plus 8. Now you differentiate this 2 by s square plus 4s plus 8 by using quotient rule, u by v formula. So we get this 2 into 2s plus 4 by s square plus 4s plus 8 whole square. So this is very important problem. So using the theorem and the previous first shifting property, you can do these 4 problems. Next theorem gives the Laplace transform of the function of type f of t by t. So t into f of t will be minus d by ds. Here f of t by t will be the integral s to infinity L of f of t ds. So this 1 by t under the Laplace transform is changed into the integral s to infinity. So for f of t, I have to find the Laplace transform that has to be integrated with respect to s. Let us take up an example. Find Laplace transform of 1 minus e power t by t. So here the given function is of the type f of t by t, where f of t is 1 minus e power t. So according to theorem 2, this Laplace transform will be equal to this 1 by t is changed into integral s to infinity L of f of t. F of t is nothing but 1 minus e power t ds. So you find the Laplace transform for 1 minus e power t, which is nothing but Laplace transform of 1 minus Laplace transform of e power t. Laplace transform of 1 is 1 by s minus Laplace transform of e power t is 1 by s minus a. Here a is 1, so 1 by s minus 1. If you integrate this term by term, you get the first integral is nothing but integral ds by s, which is nothing but log s. Similarly, the second term is integral ds by s minus 1, which is also log of s minus 1. So now this is of the form log a minus log b, which can be taken as log of a by b. So log of s by s minus 1 integral, this is the value of this integral, and the limits are s to infinity. So whenever you want to apply the limit infinity, you have to do one thing. You have to keep s only in the denominator in each and every term. Wherever s comes, it should be only in the denominator. Then only the term with s in the denominator will become 0 when applying s is equal to infinity. That is the concept behind this. So before applying, let us do some modification. You see the denominator, it is s minus 1. You take s outside from the denominator, you get s into 1 minus 1 by s. Now these two s get cancelled. So after cancelling these s's, we get log of 1 by 1 minus 1 by s. Now if you put s is equal to infinity, that means the upper limit, this 1 by s becomes 1 by infinity becomes 0. When you put s is equal to s, this expression remains same. So the first term is log 1 minus second term is log of 1 by 1 minus 1 by s. Since the value of log 1 is 0, we get this value as the Laplace transform for the given function. Let us take up another example. Find Laplace transform of cos 2t minus cos 3t by t. This function is exactly of the form f of t by t. Therefore, according to theorem 2, this Laplace transform will be integral s to infinity. This 1 by t is changed into integral s to infinity, and we have to take the Laplace transform for cos 2t minus cos 3t, which is nothing but the numerator f of t. So this is equal to integral s to infinity L of cos 2t minus cos 3t ds. The value of L of cos 2t is s by s square plus 2 square minus L of cos 3t is s by s square plus 3 square ds. How do you evaluate this integral? See the numerator, it is s ds, but the denominator is s square plus 2 square. If you differentiate s square plus 2 square, you get 2s ds. So you know the value of the integral f dash of x by f of x dx equal to log of f of x. That means if the numerator is the derivative of denominator, then the value of the integral is log of denominator. So using that standard result, you can write the value of these integrals. So the only thing is that here in the numerator the constant 2 is missing. So we should have 2s, then only we can use that result. So to have 2 in the numerator, you just divide and multiply each and every integral by 2. So this could be taken as 1 by 2 integral s to infinity 2s ds by s square plus 4. Similarly, second one. So the value of this integral is log of s square plus 4. Similarly, the value of the second integral is also log of s square plus 9. Of course, we have a constant 1 by 2 in front of each and every integral. So 1 by 2. So if you take 1 by 2 outside from these two terms, you get 1 by 2 into log of s square plus 4 minus log of s square plus 9. This is of the form log a minus log b. This can be taken as log of a by b. We want to apply the limit infinity for s. So as we have seen in the previous problem, you take s squared outside from the numerator. The same s squared should be taken out from the denominator also. So after cancelling these s squared, we get 1 by 2 into log of 1 plus 4 by s squared by 1 plus 9 by s squared. If you apply the limit s is equal to infinity, this 4 by s squared and 9 by s squared becomes 0. So we get 1 by 2 into log 1 minus 1 by 2 into log of, if you put s is equal to s, you get the same expression, 1 plus 4 by s squared by 1 plus 9 by s squared. The value of log 1 is 0, and we are left with this answer, minus 1 by 2 into log of 1 plus 4 by s squared by 1 plus 9 by s squared. So using the theorem 2, you can now try to solve these two problems. Let us take up another theorem, last theorem. It states that Laplace transform of integral 0 to t f of t dt equal to 1 by s into L of f of t. That means the integral under the Laplace transform is changed into 1 by s, and for the integrand you have to take the Laplace transform. So this integral is changed into 1 by s, and for this f of t you have to take the Laplace transform. So this is all about theorem 3. So using this theorem we will take up only one important problem of finding the Laplace transform of e power minus t integral 0 to t cos t dt. So Laplace transform of this expression e power minus t integral 0 to t cos t dt will be equal to Laplace transform of, so here look at the given expression, it is of the type e power minus at into f of t. So according to first shifting property, Laplace transform of e power minus at into f of t will be equal to L of f of t, where s tends to s plus a. So here f of t is this integral 0 to t cos t dt. For that you have to find the Laplace transform, and in that you have to take s is equal to s plus 1. Okay, so now you take this one, Laplace transform integral 0 to t. How do you find Laplace transform of integral 0 to t? According to theorem 3, Laplace transform of integral 0 to t, this integral 0 to t becomes 1 by s. 1 by s, and for the remaining integrand you have to take the Laplace transform of t cos t. Now you look at this Laplace transform of t cos t. It is of the form L of t into f of t. According to theorem 1, Laplace transform of t into cos t will be equal to minus d by ds of L of cos t. That means t under the Laplace transform is changed into minus d by ds, and here for cos t you have to take the Laplace transform. Clear with this? So minus d by ds of this t is changed into minus d by ds, and L of cos t will come here. So the value of L of cos t is s by s square plus 1. You differentiate s by s square plus 1 with respect to s with negative sign. It is of the form u by v. So its derivative is v into derivative of numerator, that is 1, minus u is s into derivative of denominator is 2s by v square. If you simplify, you get this value 1 minus s square by s square plus 1 whole square. Already there is an 1 by s minus 1 by s we have here. So ultimately you have to replace s by s plus 1. Wherever s comes, you just replace it with s plus 1, you get the final answer. So using the above theorem, you can solve this problem. You can find the Laplace transform of integral 0 to t e power minus t sin t dt. Next, let us take up periodic function. It is another important topic from this unit. When a function is said to be periodic, and what about the period of the function? A function f of t is said to be a periodic function if f of t plus a equal to f of t for all values of t, and the least value of a is said to be the period. Okay, this is the simple definition. You might have seen it in physics. The Laplace transform for periodic function is different from the other functions. Whenever f of t is a periodic function with period a, one result gives the Laplace transform of that kind of periodic function. It states that L of f of t equal to 1 by 1 minus e power minus as integral 0 to a e power minus st f of t dt. This is a very important result. Whenever f of t is a periodic function with period a, its Laplace transform will be this 1 by 1 minus e power minus as integral 0 to a e power minus st f of t dt. Proof is there for all the results we are seeing in this Laplace transform. If you refer book, you can find every result with proof, but since proof is not that much important, I skip the proof then and there, and I give you the problems using the results only. Okay, so now let us take up an example for this periodic function. Find the Laplace transform of the function f of t, which is defined by t in the interval 0 to b, which is equal to 2b minus t in the interval b to 2b, with f of t plus 2b equal to f of t. Whenever you are given a expression identity like this, f of t plus 2b equal to f of t, it means that f of t is a periodic function with 2b as its period. Okay, so it is understood. Okay, so it is clear from the given definition of the function f of t that f of t is a periodic function with period 2b. So therefore, using the result, we have L of f of t equal to 1 by 1 minus e power minus 2bs. Here 2b is the period, so 2b will come here, and integral 0 to 2b e power minus st f of t dt. So this integral 0 to 2b should be split into sum of two integrals, because f of t is given by means of two different values, one in the interval 0 to b, another one in the interval b to 2b. Accordingly, you have to split this into integral 0 to b plus integral b to 2b. So in each and every interval, you can substitute the respective value for f of t. In the interval 0 to b, f of t is t, and in the interval b to 2b, f of t is given as 2b minus t. So both the integrals are of the type integral uv dx. So you know the Bernoulli's formula, which gives you the value of the integral uv dx. It is equal to u into v1 minus u dash into v2 plus u double dash v3, etc., where u is the polynomial in x and v is any function of x. So here in the first integral, t is the polynomial. So you take t equal to u, and this e power minus st as v. Similarly, in the second one, 2b minus t should be taken as u, and e power minus st should be taken as v. So both the integrals are of the form uv dx. So using this Bernoulli's formula, the value of the first integral is u into v1. U is t into v1. v1 means you have to integrate e power minus st with respect to t. So the value of the integral e power minus st with respect to t is e power minus st by minus s. This is u into v1. Minus second term is u dash into v2. You differentiate the first term, integrate the second term. So u dash, derivative of t is 1 into v2. v2 means you have to integrate this again with respect to t. So if you integrate this again with respect to t, you will get one more minus s in the denominator, that is minus s square. Similarly, in the second integral also, you can use the same Bernoulli's formula. So here u is 2b minus t. So u into v1. The value of integral e power minus st with respect to t is e power minus st by minus s. Minus u dash is derivative of 2b minus t is minus 1 into v2 is e power minus st by minus s squared, minus s whole squared. Now we apply the limits, upper limit minus lower limit, upper limit minus lower limit. So after simplifying, you get an expression of the type 1 minus 2 e power minus bs plus e power minus bs whole square. This e power minus 2bs can be taken as e power minus bs whole square. Similarly, this e power minus 2bs, we have taken it as e power minus bs whole square. Now this expression is of the form a square minus b square. This can be taken as a plus b into a minus b. These three terms together can be taken as a minus b whole square, that is 1 minus e power minus bs whole square. If you expand this, you get this. So here you can cancel 1 minus e power minus bs, 1 minus e power minus bs. So after cancelling the like terms in numerator and denominator, we are left with 1 by s square into 1 minus e power minus bs by 1 plus e power minus bs. Here we use one trigonometric result. It states that the value of tan h x by 2 is equal to 1 minus e power minus x by 1 plus e power minus x. So here this expression is exactly of the form 1 minus e power minus x by 1 plus e power minus x, where x is equal to bs. So according to this result, this will be equal to tan h bs by 2. So therefore the Laplace transform of the given periodic function is 1 by s squared into tan h bs by 2. So using that Laplace transform of a periodic function, you can solve these two problems. So with this, the first part of the Laplace transform is over. In the next video, we will look into the inverse Laplace transform. That is the second half of this unit. Thank you.